Alrighty, guys, welcome back. Today's going to be a fun day. Today we're going to talk more about polynomials, and I'm going to share with you what I think is sort of the coolest and most beautiful piece of useful information for graphing polynomials that exists. What I'm going to show you today is kind of how I graph functions when I need to sketch a graph. So I'm happy to share that with you. Another thing, this lecture is going to be kind of intended for two classes. So my earlier class, MAC1140 section 008, I am in a very sleepy and foolish stupor, ended early. So those of you tuning in from 008 to watch this video, per the announcement, I appreciate you taking the time to do so. Feel free to skip ahead about 30 minutes because you guys missed out on the latter half of the lecture, and I don't want that to happen. To my 009 people, good morning, welcome. Let's get started, or good afternoon. Let's get started. Screen share. So your homework from Tuesday, which I know I didn't get published until quite late in the day there, isn't due today, obviously. It's set to be due next Tuesday because I didn't get it up as quickly as I wanted. But there will be another homework, which I will put up today, which will also be due next Tuesday. It's going to be the 3.2 part 2 homework. In other news, I know everybody is wanting their tests graded. I have not graded them yet, but my goal is to get York sections tests graded today. That goes for both 008 and 009 people. I'll be running by the college to pick up the scratch work for those of you who took it at the center right after this class today. All right, this is MAC1140.009, which means we're talking pre-calc, and today is the 30th of September 2021. Today we're talking more about polynomials. Specifically polynomial graphs, which is the section we started last time, 3.2. And time permitting, we may move this concept of dividing polynomials. So something that I like to tell people and that I think you should keep in mind is that polynomials are like the function version of a whole number, right? Kind of whole numbers, real numbers, rational numbers, irrational numbers. You can classify numbers. You can also classify functions. And it turns out that polynomials are very similar in their classification scheme to the set of integers, right? The whole numbers, positive and negative. They both form what's called a ring. It's the algebraic structure that they form. If you add two of them, you get another one of them. You multiply two of them, you get another one of them. But if you start dividing them, you might wander outside the space of polynomials. Just like if you divide two integers, there's no guarantee you're going to get another integer. Let me just remind you that a polynomial of degree n, and n here is a non-negative integer, is an expression of the form most of the time we'll use letters nearby p in the alphabet for polynomials, conveniently p of x for polynomial function of x. A polynomial of degree n is something involving x to the n. There's allowed to be a number multiplying x to the n. We said last time we call that guy an. And then, all the other lower powers of x are represented too. Or they could show up. If this is x cubed, there could be an x squared and an x. All of those terms can show up in a polynomial of degree n, although they do not need to. And if one of these terms isn't there in your polynomial, that just means that his coefficient is 0. So here, the numbers, the constants, such a quick period here. The constants an an minus 1, and so on, are called coefficients. An, the coefficient of the largest power of x, it has a special name. An is called the lead coefficient. We talked about this last time. A0 is called the constant term. I'm not going to write that down again, but the lead coefficient is going to play an important role in what we're going to learn about kind of first today, which is end behavior. Getting into this though, I just want to spend a second making sure we can identify the degree, coefficients of some specific polynomial. So let me generate one here. Let's call it negative x to the 7 plus 2x to the 5 minus 4x cubed plus x minus 1. Right. And I'd like to ask, what is the degree here and what are the coefficients? So what is the degree here?
Seven.
Maybe my volume is too low. I'm sorry. Gavin, what can you repeat yourself for me? I'm sorry.
I believe the degree is 7 or negative. Is it negative 7?
7 is correct. So the degree is the power, the largest power of x that shows up anywhere, right? So n is the degree here. So you look for the x with the largest power. That power is your degree. So you're correct. 7. 7 is the degree. And then the coefficients. Those would then be A7, A6, A5, A4, A3, A2, A1, and A0, right? A polynomial of degree n has actually n plus 1 coefficients. So what is the lead coefficient, A7?
-1.
Very good. It's the number attached to x to the 7. And the number that's attached to, we just have a negative x to the 7. We know that means that x to the 7 is being multiplied by -1. Okay, let me skip to A5 really quick. What is A5?
2.
Very good. A5 is the number attached to x to the 5, which is 2. And see why I'm skipping. The next one I would actually write down here for now is A3. A3 is the number attached to x cubed. That's -4. A1 is the number that's attached to x to the 1. And x on its own, that's the same as just 1x, so that's 1. And A0 is the constant term here, which is just -1. So coming back up here, this is the thing we call the lead coefficient. Okay. What about the ones we didn't write down here? What about A6, A4, and A2? What are they?
0.
Very good. They're all 0, right? We're tempted to think of this like, oh, there is no x to the 6, but there is. It's just being multiplied by 0. We don't see it. And the same is true for the other quote unquote missing terms. They all have coefficient 0. All right, so are we all comfortable with the kind of naming convention for the coefficients and how we can find them and the degree? Are there any questions about this? All right. So the first new thing I really want to introduce today is this concept of end behavior. All functions have some sort of end behavior. Polynomial end behavior is especially simple. What the words end behavior mean in the context of functions is kind of what does the function do as you put in really, really, really big values for x. It's tied to the concept of a horizontal asymptote, if you remember that from previous math classes. But polynomials are nice, simple functions. They don't have horizontal asymptotes. Their end behavior is either like, I'm gonna embarrass myself for you guys here. It's worked better when we had in-person classes, but every polynomial, if you zoom out enough, kind of looks like this, or this, or this, or this. This is the polynomial end behavior dance. You can take that to the next club or whatever. Have fun. Nobody's going to like it, but you can tell them what it is. I'm doing the polynomial end behavior dance. All right, that's enough shame. So what am I actually saying here? I'm saying that every polynomial, regardless of what's going on like in here, has some arrows at the ends of its graph, right? As you get far away from x equals 0, when we're drawing a graph, we always just say, oh, okay, and these arrows imply that the graph continues on in this fashion. So these are the possible end behaviors for a polynomial. Either both arrows point up, both arrows point down. Those are the first two little parts of the dance. Or one points down and the other points up, and there's two possible ways to do that. The end behavior here is going to be a really important tool for graphing these polynomials. So don't ignore this. This is a big deal, even though it looks really, really simple. Now, what's going on in between these things? I don't know. It could be fucking anything. Really doesn't matter. But I'm going to sketch some stuff in here just to kind of give the illusion that we know what's going on. All right, that's the idea, is that these graphs could look all sorts of wild in here, but they all have one of these combinations of arrows. The very first guy here, if I had to describe this, there's a special notation for this. The arrow on the left over here would say as x goes to negative infinity, y is going to positive infinity. And what that means is as x goes to negative infinity means as we wander really, really, really far to the left, right? Negative infinity is like over here. So as we wander really, really far to the left, what are my y values doing? Oh, well, this arrow is pointing up. So my y values just keep going higher and higher and higher and higher and higher. The similar notation for the thing on the right, I would say as x goes to positive infinity, y goes to positive infinity. Now, can anybody think of a polynomial that has this end behavior? Really simple. One of our parent functions.
X squared?
Hell yeah, x squared, right? X squared points up on both sides. So does x to the 4 and x to the 6 and x to the 8. The degree for all of those is even. And the lead coefficient for all of those is 1, which is positive. And it turns out those are the things that you need in order to identify polynomial end behavior. You need to know the degree. And you need to know the lead coefficient, or at least the sign of the lead coefficient. And any polynomial with an even degree and a positive lead coefficient will have that same end behavior up on both sides. This guy would be described in the arrow or goes to notation. That's what you'll hear me call this, the goes to notation, this stuff. I would say here as x goes to negative infinity, y is going down, right? As I wander really, really far to the left, as x goes to negative infinity, the y values are going down. So y is going to negative infinity. And this end behavior over here, I would say, as x goes to positive infinity, as I wander really, really far to the right, the y values are also going down. So y is going to negative infinity. Polynomials which exhibit this type of end behavior are those with an even degree and a negative lead coefficient. I'll go ahead and wrap up these last few. This guy says as x goes to negative infinity, y goes to negative infinity. This guy says as x goes to positive infinity, y also goes to positive infinity. And this end behavior is associated with an odd degree and a positive lead coefficient. You can think like x cubed. And then the very last guy here, this would be as x goes to negative infinity, y goes to positive infinity, and as x goes to positive infinity, y goes to negative infinity. This is an odd even and negative lead coefficient. All right. So these are all of the different types of end behavior that can be exhibited by a polynomial. The first step in drawing the graph of a polynomial is figuring out the end behavior. You draw in just those arrows, like just this and this. The next few steps involve finding the x-intercepts or the roots, and then figuring out what the graph looks like very nearby those roots. And it turns out that because polynomials have some very nice properties, which is the next thing I'm going to describe, once you know the end behavior and what we call the local behavior near the roots, you have sufficient information to draw a really nice graph. The reason for that is the following theorem. Polynomials are continuous, meaning the graph is unbroken. Another word for that is connected, single piece. No holes or gaps. And smooth. They have no points, no pointy bits. Sometimes those are called the cusps. So continuous and smooth, or continuous and infinitely differentiable, if you like the highbrow language. This puts a pretty serious restriction on what polynomials can and cannot do. There's a related theorem called the intermediate value theorem, which says if p of x is a polynomial and p of a has opposite sign to p of b, then p of x must be equal to 0 somewhere between a and b, between x equals a and x equals b. The picture that kind of goes with this second theorem is tied to the first one. I'll draw sort of two pictures here. Maybe over here is A, over here is B. So when I say that P of A and P of B have different signs, that means one of them is positive and one of them is negative, and it doesn't matter which one. So here's some points on the graph of this polynomial, and maybe the graph goes off there and does stuff like that. The idea is that you cannot get from here to here. You cannot connect these points without crossing the x-axis. In other words, you have a solution to P of x equals 0. You have a root somewhere. Because the graph has to be both smooth and connected, specifically it's the connected here, there's no way for the graph to join this point to this point without going through the x-axis, no matter how hard you try. So, there's no avoiding an x-intercept since we go from under to above the x-axis. And you could also go from above to under. It could go either way. Maybe P of A is the positive guy and P of B is the negative guy. Okay, no matter what's going on over here, no matter how hard you try, you gotta go through that x-axis if you're gonna go from above to below or from below to above. This is something we're going to rely on in a kind of subtle way down the line, but you don't need to stress about it too much. Just know that this is called the intermediate value theorem, and it is what it sounds like. You can't go from being negative to positive without being 0 somewhere in between. You can't go from being positive to negative without being 0 somewhere in between. There are a few problems in your homework set that just ask you, could this graph be the graph of a polynomial? All you got to do is think about the first theorem for that. Is the graph continuous? That is it a single connected, unbroken piece with no holes? And is the graph smooth? Does it not have any pointy bits or cusps? If the answer to all those questions is yes, then yeah, this could be the graph of a polynomial. If the answer to any one of those questions is no, then no, this could not be the graph of a polynomial. Okay. Yeah, we're ready. Okay. One more thing. This page is very theorem heavy. You remember that TFAE theorem for inverses? Here's another TFAE. Let P x a polynomial. One. C is a root or 0 of P of x. Right, the number C. 2. P of C is equal to 0, i.e. x equals C is a solution to the equation P of x equals 0. Three. X minus C is a factor of P of x. And remember what factor means. This is important. That means p of x can be written as x minus c times some other polynomial. Right, so a factor, like 3 is a factor of 24, because 24 can be written as 3 times 8. Or x minus 1 is a factor of x minus 1 times x plus 2. And then I suppose you could say the point c comma 0 is an x-intercept. Right, so this is a big deal, and I think probably most of you know this, but maybe haven't said it explicitly, and it's just nice to get it out there. These things that we've been calling roots or zeros, we know are x-intercepts, and we know the way we find them is by factoring. And then, of course, you know, if you find an x-intercept or a root, that means that p of that number, or f of that number, if your function is f, is equal to 0. That's what it means. The big one here is the connection from 3 to 1. Right? You have a root if and only if you have a factor. So this last theorem tells us that factors and roots come together. Right? If you know the factors, you know the roots. And on the other hand, if you know the roots, you know the factors. There's one more thing I'd like to say about factors of polynomials, just in general. We're not going to worry about factoring, at least not, you know, advanced factoring yet, just the stuff that we talked about yesterday, Tuesday. And this has to do with multiplicities. So to talk about this, I need to define a new term, and that is the multiplicity. So let p of x be a polynomial. And suppose p of x can be written as x minus c to some power times some other polynomial q of x. The number m is called the multiplicity of the factor x minus c, or sometimes the multiplicity of the root c. Here, q of x does not have any factors of x minus c. So this is kind of, you pulled all of the x minus c factors out that you can. The term we're defining here is multiplicity. And it turns out that the multiplicity of a factor tells you how the graph looks near that root. So you know factors tell you roots, tell you zeros, x-intercepts. And it turns out that the multiplicity of the factor tells you what the graph looks like nearby. So last theorem before we apply this shit. The shape of the graph of p of x near its roots is determined by the multiplicity. So what I'll do is I'll put the multiplicity over here and the local behavior, or possible local behaviors, over here. So if I have a root at x equals c, and the multiplicity is equal to 1, then there's really only two ways that that graph could look nearby c. So it's the graph of p of x. Either it looks like this, right? Just crossing straight through from bottom to top, or like this, crossing straight through, but from top to bottom. But basically, the polynomial p of x will look like the parent function near 0 associated with that multiplicity. So like the parent function y equals x has a multiplicity 1 root at x equals 0. And that's just a straight line. You know what it looks like. It just crosses straight over the x-axis. The parent function x squared, you know what that looks like near 0. Well, that means that any polynomial with a multiplicity 2 root, at least near that root, will look like this. It'll bounce off the graph in a kind of parabolic shape, either from above to above or from below to below. If you have a multiplicity 3 root, a factor of multiplicity 3, then near that root, the graph will look like x cubed, looks near 0. Or like negative x cubed looks near 0. It will cross, and it will cross in this kind of S shape. I'll show you the m equals 4. I don't think we'll see any higher multiplicity things, but that's the idea, is that it looks like the similar power function. So the m equals 4 multiplicity is going to look a lot like x to the 4 looks near 0. It's that like flattened out parabola, or that flattened out upside down parabola type shape. So this theorem is probably the most important. The end behavior together with this theorem is all you need to draw really nice graphs of polynomials. And I'm going to show you exactly how we do that. We'll start with a simpler example, and then we'll progress to harder examples, okay? Is anybody still writing? Need me to hold off for a minute, or can we jump to examples? All right, let's do it. So we're going to find the end behavior and local behavior near roots. Then sketch the graph. So p of x equals negative 2x cubed times x plus 3 squared times x minus 4. So this polynomial is in factored form, right? This is fully factored. This is not in that an x to the n plus an minus 1 x to the n minus 1 and so on form. The factored form is nice because it tells us the roots and the local behavior, but it makes it a little bit harder to see the end behavior. Let's get that out of the way first. So I need to know what is the lead coefficient and what is the degree. Can anybody help me with the degree?
Three.
3 is a reasonable thought, right? Because the largest power of x I see anywhere here right away is this x cubed. But remember that the degree comes from like this form, right? Where it's all multiplied out, So my polynomial here is not all multiplied out. So we've got two choices. We can either go through the process of multiplying that whole thing out, which would mean like foiling this, then distributing this, then distributing this, or we can imagine foiling everything out, distributing everything, and ask ourselves, what would the highest order term look like? So forget about the x cubed for a minute. If I multiply all this out, x plus 3 all squared, the highest order term there is just x squared, right? It would be x squared plus 6x plus 9. We know that. But this guy would have an x squared as his highest order term. So then when you multiply these two together, the highest order term would be x cubed, right? So you'd have like this x times the x squared you get from this guy. And then if you multiplied this x cubed all the way through, you would have x cubed times x cubed, which is x to the 6. Does everybody see what's going on there? So you just imagine multiplying everything out. You don't have to track all the terms, you just have to track the highest order term. So what's my degree?
6.
Yeah, 6. And what about the lead coefficient?
-2.
Very good, that's -2, right? So if I cover up the -2 here, I know multiplying all of this stuff out, I would have x to the 6 plus a bunch of other shit. So then when you distribute the -2, you would have -2 times x to the 6 plus a bunch of other shit. So yeah, the lead coefficient here is -2. All right, that means my end behavior must be, let's see, I've got an even degree and a negative lead coefficient. So as x goes to -infinity, y goes to -infinity, and as x goes to +infinity, y goes to -infinity. The arrows point down on both sides. Right? Even degree, negative lead coefficient. What are the roots? So this polynomial is fully factored. We know each factor tells us a root. What root do I get from this factor?
Is it +4?
Yeah, 4, right? X minus c is a factor. Is that theorem? X minus c is a factor means x equals c is a root. So one of our roots here is x equals 4. What's his multiplicity? Remember, the multiplicity is the power of the factor from which the root comes. So what's the multiplicity of the root at 4, the root that comes from this factor? What is the power of this factor?
1.
1. Okay. What is the root I get from the middle factor, the x plus 3 all squared?
-3.
Very good, -3. Because that factor would be 0 and x is -3. What is his multiplicity?
2.
2. Very good. Alrighty. And then from that first factor, the x cubed. Remember, x cubed is the same as x minus 0 all cubed. People just don't like to write the 0. So what's the root associated with this factor?
0.
Yeah, that's 0. And his multiplicity?
3.
3. All right. Now we have the end behavior and the local behavior near the roots. We have everything we need to draw a really dope graph of this function. I'm going to give myself a little more space down here than up here because I know both of the arrows point down, and I'll start just by drawing in those arrows pointing down. What follows is not an exact science, but it will get us a graph with the correct shape, the correct number of mins and maxes, the correct x-intercepts. Lots of things will be nice. Once you've drawn in the end behavior, those arrows, you plot the roots. So I've got one at 4, I've got one at 0, and I've got one at -3. Let me call this here -3. This, of course, is 0. And +4, I'll call this. Okay. Here's how I do it. Start at the far left side. You know that you've got an x-intercept right here. That means you're either going to cross the x-axis here in some way, or you're going to bounce off the x-axis here in some way. But you got to touch that x-axis, and you have to come from this arrow. All right, this arrow is pointing down, and this is the very first x-intercept we run into going from left to right. So the graph has to connect this arrow to this x-intercept because we've got to be a smooth and connected graph. I know that the -3 root is a multiplicity 2 thing. So either it's going to bounce like this, looking kind of like x squared, only shifted over there, or it's going to bounce like this, bottom to bottom or top to top. Which one? Is this guy going to bounce a top to top like this? Or is he going to bounce a bottom to bottom like this?
Bottom to bottom.
Good, because it has to connect to this arrow, which is down here. So I know that the local behavior here is like this. I don't know much else, but I know that near that x-intercept, this thing looks a lot like x squared because it's multiplicity 2. And it's going from down to down because it has to connect to this arrow. All right, then we move to our next root, this guy, which is x equals 0. X equals 0. He's a multiplicity 3 root. So he's either going to go like this, like kind of the S curve from down to up, or like this, the S curve from up to down. Which one am I going to have here? The down to up S curve or the up to down S curve, and why?
Down to up because the function needs to be fluid or like connected.
Got to connect to this piece right here, right? And this piece is below the x-axis. I don't have any other roots between -3 and 0, so it's not like it can cross over and then do an up to down. If it were to cross over, then that would mean we've got another root here, right? That's that intermediate value theorem. So because this graph is going down here, we're negative, I know I have to arrive here in a negative fashion, which means the local behavior there is like this. And then we play the same game for the last guy over here, 4. So x equals 4 is a root, the multiplicity is 1. That means it either crosses like this or like this. And because we're arriving from above and we have to leave below, I know it's like that. And you can see how once you've got this, it's really not that hard to go do-do, do-do-do, do-do-do, do-do-do. You just connect the pieces. It has to be smooth and connected. So, you know, you've got to have like a little turnaround here. That's the only way you can bounce off of this and then come back here in a smooth and connected fashion. Similarly, over here, I know I've got to leave coming out like this, and I know I've got to come back over here like this, so it's got to have a little turnaround. This graph is not perfect. Say that at the start. This graph is not perfect. Like maybe this valley goes way the fuck down, or maybe this hill goes way the fuck up, and that's not reflected in the graph drawing. But a lot about this graph is correct. Specifically, it has the correct number of local maxes and local mins. My graph has 1, 2 local maxes and 1 local min. I'm going to show you the Desmos version of this graph in a second. You'll see it's very, very similar. Also, it has the kind of correct squiggly behaviors, right? The correct shapes, which is very important. So let's take this graph and compare it to what's produced by Desmos. All right, now, like I said, my y-axis could be really crazy. So I'm gonna go from like negative 500 to 500 just to, whoa, shit, look at that. Look at that, 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 look at that. Not fucking bad. Now, yeah, there's the actual graph blows way up to like 2000 there, whereas mine, you know, doesn't. But look, I've got 1 local max here and another local max here. 1 local max here and another local max here. I've got 1 local min here, 1 local min here. Correct number of mins and maxes. Correct number of x-intercepts. Correct shape nearby each x-intercept, right? This is kind of that S-curve shape. This is that S-curve shape. This is that bouncy parabola shape, the bouncy parabola shape. And the straight cross, the straight cross. So we did a damn good job here, especially for how little work we did, right? This was not hard work. I think that's kind of magical. And particularly, you notice I didn't plot any points, right? I made no table. I didn't ever sit down and go X, Y, X, Y, X, Y, X, Y. There was no guessing involved. That's really nice. At no point did I go, I don't know if this goes to this or to that. It's very clear. If you want to enhance a graph like this, you can plot some points. Like if I was trying to draw a really, really good graph here, I would plug in -2 and -1 and just see how deep this valley is, or try to get a feel for it. And I would plug in like 1, 2, 3, try to get a feel for how tall this hill is. That would do me well. But honestly, this is really good. This is like, for the purposes of calculus, this is not bad. Certainly for our purposes, it is more than sufficient. So before I move on, are there any questions about how I got this purple graph, why it looks so much like this Desmos graph, what's different about them, why, all that stuff?
I just have a question on if we get tested by this, can we do a graph like that? Does it need to be like incredibly accurate?
If this was a test question, like use end behavior and local behavior near roots to sketch the graph, this right here would be 100%, 10 out of 10. Perfect. In fact, anything more detailed would be suspicious. Make me think maybe you're using a graphing utility, but of course that's not necessary. Yeah, no, this would be more than enough on a test. Fair question. Other questions on this? Are we all comfy with how we found the degree, how we found the lead coefficient, how we found the roots and their multiplicities? Okay, I have a fun fact for you. When it comes to finding the degree, the degree of a polynomial is always equal to the sum of multiplicities of its roots. So like if I wanted to find this degree, the degree of this polynomial, which was 6, remember, without imagining multiplying it all out, this fun fact gives us another way to do that. I can look at each of the factors here. This is multiplicity 3, this is multiplicity 2, this is multiplicity 1, and just add those up. 3 plus 2 plus 1 is 6. You don't even need to imagine multiplying it out. So this fun fact makes this process even faster. Now, imagine I give you an arbitrary polynomial. What do you think would be the hardest step to getting a good graph like this? I just start writing down, 5x cubed minus 7x squared plus 3x minus 2. What do you think is going to be the hardest step in getting this picture from that polynomial? What's already been done here?
Factoring.
Yeah, they factored this thing for us already. Factoring, it turns out, is a bitch and a half. It's really hard. Like, even computers are bad at it hard. So in the next few examples I'm going to show you, we'll do a little bit of factoring. The sections that come after this on dividing polynomials, the rational roots theorem, synthetic division, all of those are about factoring polynomials. It turns out to be an incredibly hard problem, especially for large degree. Did I talk to you guys about Galois on Tuesday? Galois' work is connected to the factoring problem. All right. Let's do the same thing. Use end behavior and focal behavior. Sketch give x equals, and give me just a minute here. I think we're going to go for x to the 4 minus 4x squared plus 4. Lots of 4s. All right, so same thing. Let's do it with this guy. Here, hang on. Let me change that just a little bit. My brain is just not working today. Cubed, and let me make this an x squared. Sorry. So x to the 4 minus 4x cubed plus 4x squared. We'll do this guy. I can write down the end behavior stuff because it's it's in this nice form, which is easy to see the degree and the coefficient. But then to get the other stuff, I'm going to need to factor it. So the degree here is 4, right? That's the largest power of x. The lead coefficient is 1. So my end behavior is going to be, as x goes to negative infinity, y goes to positive infinity. And as x goes to positive infinity, y goes to positive infinity, up on both sides. The other thing I need is the roots, right? And all the information around the roots. In order to find those, I need to factor this thing. So I've got x to the 4 minus 4x squared cubed, plus 4x squared. And the first thing I see here that I can do factoring wise, well, maybe you tell me what nice easy factoring step can I use here?
0.
There is so there is a factor that will give us a root of 0. The factor that we're going to extract here is x squared. So first I need to factor. And when I factor out an x squared, this will become x squared minus 4x plus 4. Can I factor this any further? Does x squared minus 4x plus 4 factor? We talked about this on Tuesday. Looking for two numbers that multiply to positive 4 and add up to negative 4. Those are?
-2.
Good. So this is x minus 2 times x minus 2. So the fully factored form here is x squared times x minus 2 squared. I just got 2's all over the place. So what are my roots? What are their multiplicities?
0 and
Yeah.
2.
Very good. 0 and 2 are the roots. And what are their multiplicities?
2.
Yeah, both are multiplicity 2. All right. This is all the info we need to draw a nice graph. Here it goes. We said the end behavior is up on both sides. I've got two roots, one here at 0 and another here at 2. And they're both multiplicity 2 roots. So they both have to do that parabolic bouncy thingy. Since I'm coming in here from above, I know this has to be an up to up bounce. So I'm leaving here going up. That means this also has to be an up to up bounce. I'm putting the pieces together, the graph, then must look something like this. Is it going to be perfect? No. Is it going to be plenty good? Yes. Could this hill be much, much taller? Maybe. These valleys, though, they have to sit on the x-axis, and everything has to connect to these arrows. So really, it's got to look like this. Let's see what Desmos says. Cute. So that hill there is actually very, very small. That's what we're seeing here. So if my y-axis, I scale, oh no, things are just scaled crazily now. Yeah. Set things to like -10 to 10. Yeah, here we go. That's more like your normal scale. Again, yeah, this hill turns out to be a lot smaller than our hill looked like, but it's the correct shape. It's got the correct number of mins. We've got a min here and a min here. It's got the correct number of maxes. We've got one max here, and it's got that overall W shape like we thought it would. So this is a perfectly acceptable graph, and yeah, this would get full credit on the test. Actually, I would ask you for one more point. So my usual rule is 3 points if it's just a single graph. But you take this together with any other single point of information, maybe find that is P of 1. 1 minus 4, 4, which is 1. So this point right here, I could say is actually 1 comma 1. And that fixes our scale issues. It's just got a silly scaled y-axis. Let's work it back the other way. Let me give you a graph and ask you, can you tell me a polynomial that might have this graph? So I claim that this is the graph of some polynomial. Let's say that this y-intercept up here is like 5. Graph y equals p of x. Just looking at the graph, what can we say about the thing? What can you tell me about, for example, the degree of this polynomial, just looking at the graph?
Has a degree of 3 because the end is different from the beginning.
Yeah, or
Endpoint,
at least must be an odd degree, right? Because we're going down on one
Yeah,
side
that's a
and
better
up
way to
on the
put it.
other. And 3 is a reasonable guess, right? This looks like a multiplicity 2 root. This looks like a multiplicity 1 root. I would say, yeah, degree 3 is correct. What can you tell me about the lead coefficient?
It's positive.
Good, the lead coefficient's definitely positive because we're going down on the left and up on the right. What can you tell me about, okay, so degree. Definitely odd. Looks like 3. The lead coefficient. Definitely positive, right? Okay, what about the factors? What about the roots? Remember, roots and factors come together. You know one, you get the other. Before we were given the factors and we had to come up with the roots. Now I'm being given the roots. I need to come up with the factors. So somebody tell me a factor of this polynomial.
X plus 2.
Very good.
And
And
X minus 1.
very good, x minus 1. And in fact, we can say the multiplicities, right? This factor is coming from the root at x equals -2, which has m equal to 1. And this guy is coming from the root at x equals 1, which has m equal to 2. So the x minus 1 factor should be squared. Thus, p of x is looking something like, I'm leaving space there for a reason, x plus 2 times x minus 1 squared. I've left space here for the lead coefficient. Let me show you something cool in Desmos. I have a slider for A. This actually looks a lot like our guy, right? But so does this. So does this. Sort of, so does this. And sort of, so does this. So there's lots of possible polynomials that have this graph shape. And what you have to do is allow for this lead coefficient. Because you know he could be anything as long as it's positive. And then we need to solve for that lead coefficient using whatever bit of extra information we were given, right? So it's very hard for me to say right away whether I'm looking at, you know, this guy or this guy or this guy or this guy or this guy, right? They all have the correct local behavior near the roots. And as long as I keep this A positive, it'll have the correct end behavior as well. So is A, you know, 5.7, 4.3, 2.3, 3.1. How do we figure it out? What piece of information from this graph have I not yet used in coming up with this formula for P?
That we know it's a positive.
It's true, I really haven't used the fact that the lead coefficient is positive. That is true, you got me there. But look, more specific information here, like quantitative information, numbers.
Oh, the point at the 5.
Yeah. 0, 5 is on this graph. So we need to find A. We know the point 0, 5 is on the graph. And that means P of 0 is equal to 5, right? A comma B, remember the original TFAE, the first TFAE theorem we had this semester? A comma B is on the graph of F, means F of A equals B. Well, here's the point 0, 5. It's on the graph of the polynomial P of X. So that means P of 0 has to be equal to 5. This is where I'm using that y-intercept. And now what is P of 0? Okay, well, P of 0 is A times 0 plus 2 times 0 minus 1 squared. And that's equal to 5. Right? This stuff that I just wrote down on the left-hand side is P of 0, because P of X is A times X plus 2 times X minus 1 squared. I'm just plugging in 0 here and saying, I know that should be equal to 5 because P of 0 is 5. Now this we can use to solve for A. 0 plus 2 is 2. 0 minus 1 is negative 1. Negative 1 squared is positive 1. So this says, I'll write it out, A times 2 times negative 1 squared equals 5. And that left-hand side, negative 2 times negative 1 squared, that's 2A equals 5. So A has to be 5 pounds. Hence, P of X is 5 halves times X plus 2 times X minus 1 squared. That's it. So if you have the graph, it's relatively easy to come up with the factored form of the polynomial, except you don't necessarily know the lead coefficient. You'll have to solve for that. But the graph, you can see the roots. The roots tell you the factors, and that tells you the majority of what you need. And to find that lead coefficient, you need some other piece of information. It doesn't have to be the y-intercept, could be any other point on the graph. Anything that tells me, oh, P of something is equal to something else, like some actual numbers I know that I can plug in and solve. In general, the factored form of a polynomial looks like this. You have the lead coefficient out front, and then all the factors that you have associated with each of the roots, each one with the correct multiplicity. There will be questions on your next test that poke at each of these things, right? Can you go from the graph to the factored form of the polynomial? Can you remember how to solve for this lead coefficient, or that this lead coefficient could be there? Can you go from the factored form of the polynomial to the graph? And then sort of the big deal is going to be factoring the polynomials, actually factoring the polynomials, which is quite hard. Now, how much time do we have? We have 6 minutes left, which is almost enough time for me to introduce the next section, but maybe not quite. Fuck it, let's try it. Yeah, let's at least get the language in here, and I can show you a little bit long division with polynomials. So, you know, factoring is intimately related to dividing. All right, when you factor something out, it's like you're dividing each term by that thing. Well, if you're trying to factor a big polynomial, one way to do that is to try and divide that big polynomial by some factors and see if you get something nice. So we can divide polynomials similarly a lot like dividing integers. You remember in like second grade when you first learned how to do long division, instead of showing you how to do like decimal arithmetic, they said, and here's the remainder, right? Like 11 divided by 5 is 2 with a remainder of 1. Well, it turns out that's the smart way, right? That's way better than like this decimal bullshit. And that's how we think of it regarding polynomials. So what did I say here? 11 divided by 2. I can think of that as 5 with a remainder of 1, and I would write that as 1 over 2. This number right here, the thing I'm dividing by, is called the divisor. This number right here, the main part of the output, is called the quotient. And the 1 up here is called the remainder, and this 2 down here is that same divisor. There's actually a very important theorem in abstract algebra which says, given any two integers, P and D, let's call them, we can write P over D is equal to Q plus R over D for integers Q and R with 0 less than or equal to R less than or equal to, or strictly less than, I should say, strictly less than D. So when you divide one number by another number, one integer by another integer, you get an integer, right? The number of times 2 goes into 11 is 5, that's your Q. And then some remainder. And so you can always write P over D as Q plus R over D, where R is the remainder, and that remainder is always smaller than the number you're dividing by. This works for polynomials also. Given any two polynomials, P of X and Q of X, this is called the Euclidean algorithm, by the way. One can find, oh shit, no, sorry, not P of X and Q of X, I'm sorry, P of X and D of X. One can find polynomials Q of X and R of X such that P of X, it's the exact same thing, just restated with polynomials. P of X over D of X is equal to Q of X plus R of X over D of X, where the degree of R of X is smaller than the degree of D of X, strictly small. The fact that you can do this with polynomials the same as you can do this for integers is literally the statement that the ring of all polynomials is what's called a Euclidean domain. It is a ring where you can do division in the normal way. Now, this doesn't really help you do the division, though. It just tells you the division can be done. So how the fuck do you do the division? How do you divide two polynomials? Well, it's very similar to how you divide integers, and I'll show you. The only way to really show this is through examples. Trying to write out the rule would be weird. So divide p of x equals, let's do just one example here, 6x squared plus or minus 26x plus 12 by d of x equals x minus 4. And write the result in the form p over d equals q plus r over d. All right, here's how you do it. 6x squared minus 26x plus 12 goes here. You write your normal sort of long division symbol from second grade. And the divisor, d of x, goes over here. So this is how you actually do the division, right? It's a looping algorithm. You do like the same sort of steps over and over again. And at each loop, you pay attention only to the highest order term. So I ask, what is 6x squared divided by x? I don't worry about the 4, and I don't worry about the other terms here. In other words, what do I need to multiply x by in order to turn it into 6x squared? Well, 6x, right? 6x times x would be 6x squared. So you put that up here. Then you actually multiply this by this whole thing. So 6x times x is going to be 6x squared. 6x times negative 4 is going to be minus 24x. And then, and then you subtract one whole row from the other whole row. That's why I'm putting the parentheses there. I strongly advise you do this too. And then you go through like this. 6x squared minus 6x squared is 0x squared. Negative 26x minus negative 24x is negative 26x plus 24x, which is negative 2x. And then you've got a plus 12 here. There's nothing to subtract from that, so the 12 comes down. Everybody with me so far? That was one loop. Now you do it again. What do I need to multiply this x by in order to turn it into negative 2x? In other words, what is negative 2x divided by x? Well, that's negative 2. Now you take just this guy, the negative 2 that we wrote down just now, and multiply everybody here by that. So that's negative 2x, and then negative 4 times negative 2 is plus 8. And you subtract. The first term should always cancel perfectly. That's by design. So negative 2x minus negative 2x is negative 2x plus 2x is 0. 12 minus 8 is 4. And you're done. Because there is no polynomial that I can multiply x by, no positive or non-negative integer power of x, to turn it into 4. So we're done. This is your remainder. This is your quotient. And of course, these are p and d. So the result is that p of x over d of x, which is 6x squared minus 26x plus 12 over x minus 4, can be written as 6x minus 2. That's the nice quotient, plus your remainder, which is 4, over your divisor, which is x minus 4. That's it. That's it. This is your q of x, r of x. It's just a constant in this case, and this is your It's not too bad, right? The actual division itself is not that hard. It's really not. This is called long division. There is a synthetic short division. I'll show you that next time. I think that's all I want to hit you with right now. So I'm going to give you some more homework. It's going to involve the rest of 3.2 and a few problems from 3.3 where you have to use some long division. It turns out that division is one of the nicer ways to try and start factoring a polynomial, right? Like if x minus 4 had been a factor of 6x squared minus 26x plus 12, we would have gotten a remainder of 0. And we would have learned that 6x squared minus 26x plus 12 divided by x minus 4 is equal to some nice polynomial, which would be a really good step on the way to factoring it. I'll let you think about why that's the case, and I will show you explicitly why next Tuesday. That's all I've got for you guys today. So I hope you have a lovely weekend. Please take a look at WebAssign. There's more homework for you up. All of it will be due on Tuesday at the start of next week. So both the homework that I released for you earlier this week and the homework I'm releasing today are going to come due Tuesday. I know that's a little abnormal, but I wanted to give you extra time on the previous one. Going to do my best to get your tests graded for you today and get those scores in. And yeah, that's it. All righty. Take care, guys.
Have a great day, sir. Thank you.